on spatial autocorrelation for IMGT 699 spatial regression analysis. Share the slides here. There's a slide deck. We're going to cover today an overview of spatial autocorrelation, an example kind of that shows a little more clearly how spatial autocorrelation works. Talk about how we measure and communicate spatial autocorrelation using the Morane's eye, and then some visual products like a Shin scatter plot. So autocorrelation overview, spatial autocorrelation is the level of interaction we experience between observation based on spatial proximity. Closer observations are more related with each other. This goes back to Tobler's law that while all things are related, things which are close are more related. The degree to which this applies is what we refer to as spatial autocorrelation. Spatial autocorrelation can be positive or negative. Positive refers to that clustering, that like near like, whereas negative would be some sort of dispersed pattern. We're not going to focus too much on negative. It's not something we would see in our type of data. But then you also have non-significant autocorrelation, and this would be where observations are independent, at least in the spatial realm. And why it's important, traditional statistics assume that all observations are independent. So if they are actually related, in this case spatially, that kind of violates some of those assumptions. So we need some way to account for that relationship. So to determine spatial autocorrelation, it's not something you could just plot out and look at. Sometimes our eyes deceive us on if a map shows like a clustering. We actually have to devise a mathematical test for it. One thing that we've referred to this earlier in the class is the concept of spatial weighting or neighborhood analysis. But we need to define, what our neighbors are. What measure of proximity are we using to determine this correlation? This would be binary. All neighbors within a certain number of kilometers are considered your neighbors, and we're looking for if those neighbors, the ones you consider closer in proximity, if they have a correlation to the observed value of some value x. So the relationship between all the values, that's the spatial weights matrix, usually denoted with a capital W. And across that spatial weights matrix, in any one row, when you row normalize it so that the row adds up to 1, if you times that by all the other observations, so if you're concerned with row I, which will give the spatial weights for all the neighbors relative to observation I. And then it would be across, from left to right, observation 1, 2, 3 to n, how they relate to observation I. When you times those by if you're looking to check the correlation of some measure, we'll look later in a measure of democracy amongst nations, how this will give the spatial average of all your neighbors and their measure of democracy. We refer to this as a spatial lag variable. And then just the relationship between the actual observed and then that cumulative average of all your spatially weighted observations, the more correlated it is, that would be the measure of spatial autocorrelation. So for an example, to take this from the Ward textbook, social scientists like to study what impacts democracy in a country. This is looking at national level data and using a commonly used, developed measure of the democracy in a country from a -10 to a +10 that they can assign to any country. Traditionally, since the post-war era, there's been an assumption that higher GDP per capita would equal higher democracy scores. But there were some variance in this measure, specifically like the Gulf states became very rich, but they're not very democratic. At the same time, there's some European states who don't have a lot of money, but because it seems like they're in close proximity to the other European states, which are highly democratic, that they're pulled up. So a traditional regression model doesn't account for this spatial association. So we're going to try to develop, first just check, does, today we're just looking at the autocorrelation, and this will build into spatial regression where we'd actually be able to include a spatial factor in a regression model creation. So we want to try to find out does proximity to other high or low democratic scores have an influence on the democratic score of any one country. So this is just showing the source data, and then a model. I ran it on the overall set, a linear regression for the democracy score, and this includes every country, but it had to cut off the table here in the graphic, and how GDP factors into that. So it's not it's not that significant. It shows on here it's to at least 0.01, but the adjusted R squared is only 0.0245. So there's some variance, some deviation from a pure model, and you can see that graphically here. That logged GDP, or that democracy versus that the GDP. While there's some correlation, it's not very strong. There are a lot of outliers in this set. So how do we develop a test to see if there's some sort of influence based on your neighbors? So the first thing we do is the spatial weights development. Here's an example just showing some of the countries. What they did for this example is it's a binary determination if you're a neighbor or not, just based on if you have a border within 200 kilometers of some other part of the border. It'd be like that'll give you a 1 and a 0 if it's not. This shows here, this is a row standardized, so that means across the row, it shows Denmark and the other countries, they're 1/3 because it's taken over the total. So if you created a lag variable just within Europe, Denmark would be the mean of the democracy score in Germany, Norway, and Sweden. And we would compare their score to a third of Germany's score, a third of Norway's. That would be the lag variable. So this, when you times that across from the observed democracy and then the lagged democracy, that average of all the neighbors, you can get a table of the observed and the lag variable. Here it shows the highs and the lows. You can see like Bahrain has a -8 democracy, but the sum total of all its neighbors of any country with the border within 200 kilometers of it is a -10. So just looking at these extremes, you can kind of see a high, that there's some sort of relationship. Same thing on the other end. The highly democratic countries towards the bottom are associated all their neighbors. In Portugal, all its neighbors on average are 10. Same with Ireland, and France is a 9, and their neighbors are all 10s, for example. So we can plot this out. This is just a generalized example. This isn't the actual data. I'll show that in a minute. This is where we plot out observed versus lag variables. This is you can do this as a standardized plot, meaning if your observed variable is 1 sigma, 1 standard D above, and you're comparing that to what its relative lag variable is based on that observation. Is it 1 standard D above, or how close does it come to being? If everything's right on this line, they refer to the slope of this chart is the Moran's eye. This is the measure of how influential your neighbors are. And then there's also a significance value, a p-value associated with it too, if it's very tight. So if you had a perfectly sloped 1 and a p-value of not, that you're 100% influenced by your neighbors, that there's no variation at all. But you can see, I mean, this shows, just as a generalized example, a highly spatially autocorrelated data set. So we can take that democracy data we were looking at before and run it. This is actually more complex, called a Shin scatter plot, which shows in addition to the boxes for 1 sigma and 2 sigmas, it plots in a rug plot, which just shows the significance of the plotted trend line, the regression line there through the middle. So that the tighter that rug, if you're comparing multiple measures visually, the closer it is to just a line would be the more significant. So a really wide one would show the margin of error, the confidence interval that plot could be. Obviously, if it includes the 0, 0, there's a chance within the confidence interval that if it includes a slope of 0, that it's actually an insignificant Morane's eye, or there's some chance of it. So here, even the low slope, I don't know if it shows the cursor on here, is above the 0, 0 plot. And I can run a regression comparing the observed to the spatial lag variable. And so the Morane's eye would actually be the slope of this line, which 5.7 to the -1, so 0.57. Roughly, it's kind of like R squared, not quite equivalent, but this is saying your spatial lag variable explains 57% of the variance can be explained by spatial factors. The other variant, so the rest doesn't have a spatial influence. And here it's highly significant. Obviously here it's showing there are a lot in this high quadrant, just in the variables of high democracy, in the within 0 and 1 standard D, and also have a high lagged democracy. So what this leads up to is when we test and we notice there's this spatial autocorrelation, that would cause us to violate some of our standard statistical assumptions. So we need to develop a methodology for including this lag variable within a regression model so that it accounts for the interdependence between observations. So actually what this shows here is just a basic equation where you might say democracy is a function of some intercept beta weight plus a beta weight for GDP, like the X1, but then plus a lagged measure of democracy. Rho is just how we use a coefficient for that spatial lag term, that WI times Y of I is the spatial lag term. That's the W is the spatial weights matrix. The Y is the set of other observations. The spatial lag it never includes YI of one observation, and then also in an error. And the rho would be how much influence does that spatial lag variable have in the overall model. And that's what we'll go into in the next class, specifically the spatial regression, how you develop this model. There's some peculiarities, especially things we have to add. It's not just standard linear regression. So that concludes this broadcast on spatial autocorrelation. If you have any questions, let me know. Thanks.